convenient.
Okay.
Because
so the live
I personally have 2 exams.
So
yes,
if we do it on Tuesday, do you think it's gonna be good? Next Monday probably. I need to correct you, right?
Would Thursday be a problem? Yes, Thursday will be a problem.
Yeah, because your final exam is on Friday. How do you want to submit your work on Thursday? And listen, I have an idea. How about I highlight this one and I'll get back to it in a moment. Since I need to discuss Lab 9 today, you will look at it and you can decide how many days you need. Okay, so I will get back to this item. For the review session, I'm not sure if it's gonna be an actual meeting or probably I'm gonna send you some problems with answers to try, and then you meet with me in case you have questions. So probably we're not gonna meet on this day, but I'm gonna give you prior, like before December 1, like something like, I remember I promised to give you general multiple choice questions for you to practice. Do you remember? So probably I'm gonna send you this and you ask me questions if you have. All right, so this is something just to make it clear for us. So the question is live or not? We don't know yet. Okay, all right. Now, Friday, December 4 at 7 p.m. Celine, are you with us? Wasn't it you who has issues?
Yes,
Okay, Celine, yes, I remember that. Anybody other than Celine has an exam on this time and day? By the way, nobody emailed me about that. Nobody. I hope this nobody will not talk it out on Wednesday evening. So I hope as soon as possible you tell me if you have issues with the date. And if you don't, it means that you're fine with it. Celine, do you have any suggestions? And I think if I do it later or earlier, you're gonna be unhappy anyway.
I think it's better if it's on another day.
Okay. All right, do you have anything on Saturday? I'm talking to everyone.
I don't.
Okay, if Saturday, December 5, I need to ask the other sections as well. Do you guys have any problem? Last time, did we meet at 4? Let us try at 4 p.m. I'm sure you have an exam on that day, no? All right, I'm gonna talk to the other sections. And how about I put the chat on? Where's the chat? Okay, how about I move this down and check the chat, because I'm sure probably, okay. Is the exam MCQ? I don't know yet. Can we do it Saturday morning? I cannot personally do that Saturday morning, but probably around 10 a.m. Ludovic. Okay, I need to ask the other sections. So you'd rather 10 a.m. everyone instead of 4 p.m.? 5 p.m. As you know, sometimes it's very difficult to give each and everyone the choice. And I want you to know this. I'm gonna look out what is the best timing for all the, how many sections? I think 4 different sections. So probably you're not gonna like the timing, but you need to understand that since we have 4 sections, we have many constraints. Okay, I'm gonna come back to this yellow item once we finish talking about RL circuits. I want you to see that the lab is easy, so probably this will help you come up with a deadline, and you're gonna put the deadline, not me, okay?
Doctor?
Yes.
For lab 6, I have 3 exams today, tomorrow, and Thursday. So can I do it and send it on Friday?
So you want to push this to Friday, and it's gonna be Friday, November 27th.
Yes.
Okay, which means
no one has a problem.
Okay, which means everybody can submit anytime they want, but not after Friday. Is that what you're saying?
Yes.
Okay, why not? I'm gonna do this. So I'll come back to 3 in a moment. Anybody has a question about lab 9 before we start, actually about lab 6, before we start discussing lab 9? All right, I'm gonna keep.
Yes, doctor.
Yes, you have a question.
About the values of the table, we should get it from the video of YouTube, right?
Yeah.
Just to be sure.
Yeah.
Okay.
Did you
okay,
try?
thank
Did
you.
you try? Did you try to do that? I was watching the video many days ago, and I saw Dr. Sarah taking all the measurements out loud and showing them to you. Let me know.
Yes, I did it.
Yeah.
Just to be sure.
Did you fill in all the tables?
Yes.
Awesome. Okay. So Paul, in your absence, we've been discussing the announcement I sent you, and the students wanted to modify the red line and the yellow line. We talked a bit about the item 4, and we talked a bit about item 5. Okay, so this is what we did in your absence. So can I assume we can start lab 9 and no questions about lab 6? All right, so to make it quick, let's do it over the PowerPoint. Let me start with this one. I'm gonna move this aside. I hope I answered everybody's questions. Yes. All right, so lab 9 RL circuits, we're gonna miss lab 10. Lab 10 was not actually offered for the past so many semesters for many reasons. Reason number 1, usually we don't have enough time to cover 10 labs. Reason number 2, sometimes you do not cover RLC in the course. Reason number 3, we take a lot of time with the students to discuss data analysis, and we believe the quality of what we're offering is more important than the quantity. Sometimes we would love to keep it because RLC circuits, which is lab 10, is very interesting and you need it for later on. But it's okay because you're gonna cover it in some engineering future courses, so it's okay. All right, personally, I love lab 10, but it's okay. RL circuits, the first slide is what is an RL circuit, and as you see, it's empty. So I want you please to, yes, Ratib, it's late in the evening now. So yes, tell me, what do you understand by RL circuit, and probably how is it close to RC circuits? Any ideas?
It's a circuit containing a resistance and inductance.
All right, what is an inductance?
Uh,
So this is a resistance, or what else?
solenoid.
A solenoid, we usually call it a coil.
Coil.
And this is the symbol of a coil. It looks like a resistor, بس هيك مبرومة. What else? Why do we call it L? RL is with the coil, and the coil allows the appliances to function but slowly. It dampens the path of the current. So the best way is to say that it delays the establishment of the current. It's like inertia for mechanics. Yes, so eventually the current is gonna get established, but it will oppose it for a while, so it will delay the establishment of the current. This is what the coil does. Why is it called L? We don't know yet. So how can I create a current in this circuit? And how can I close it? So probably I need a battery or any type of generator. Okay, so yeah, okay, we can have a switch, probably. You can open and close the switch and the current will flow in a certain direction. It will go into the resistor will heat up, it will go into the coil. As soon as the current goes again in the coil does something. What does it do? Why does it delay the current? Do you have an idea what happens inside the coil?
A charge.
Actually, no, because capacitors do charge. There is a magnetic field, so magnetic field.
It creates a current opposite to the.
So a current, I'm not gonna say created, is induced.
Induced.
It is opposite to who?
To the real current.
not true. Sometimes it's in the same direction of the weak current. So, but it is opposite to something. Do you remember Lenz's law? Probably you don't know it because your high school was COVID high school, so probably you have some gaps. All right, so inside a coil, the flux of the magnetic field, and I'm gonna discuss that in the next slide, the flux is gonna vary. And when you have a variation in the flux, you have an induced EMF, and EMF is something like voltage. So the coil will act as a mini battery of a certain voltage, and it will provide you with a certain current. And if the change of the flux is positive, the current is negative. And if the change of the flux is negative, the current is positive. And let me explain that. If you give it a current in this direction, let me pick a pen. If the current is in this direction and it's increasing, the induced current is gonna be opposite. But if the current that is in the yellow direction is decreasing, the purple current is gonna be in the same direction. So it is opposite to the change and not to the current itself. All right? So if the current increases, تجي ضدها. If the current decreases, تجي معها, for it to oppose the decrease. You know what I mean? All right, so any characteristics like a time constant you remember to the RL circuit, or nothing at all? Nothing at all. All right, anybody knows why do we call it L? Nobody knows. Okay, let's go now to the next slide. That is, what is an inductor? So it's only lagging for me. All right, okay, so let me know if it keeps on lagging. All right, so anyway, how about I remove my video for a moment? Video, so it's gonna lag less, I hope so. All right, so what is an inductor? So previously we said what is an RL circuit. Now what is L? An inductor is basically a coil. All right, this is a coil with an iron core. So this is an actual diagram to show you how you can have a conducting wire around a certain cylindrical core. Usually this is a good ferromagnetic material. It could be any nail, by the way. And you see the current flowing. It has to flow for the inductor to work. This is real examples of any piece of metal. Iron, for example, this could be a good inductor. This too. I hope this is many layers on top of each other to induce the inductance of the coil. Yes, this is a diagram that shows a coil with an iron core, and it shows you the direction of the magnetic field. It is basically related to the direction of the current, and you need to use your right hand rule to know how the magnetic field is pointing. But it's very important to know that inside, let me pick a very small one. All right, so inside the magnetic field is pointing in this direction, because in few moments I'm gonna study the flux, and by flux is how many, or the magnitude of the magnetic field lines going through a cross-sectional area of the coil. Also, you can think of a coil being without any iron core. So this is an empty coil without any iron core. Now let me remind you a bit about what you should know from high school, and I'm a bit scared probably you know any of this, but you're gonna study this in the course. I'm trying to zoom in, but it's not helping. It's lagging a bit because I'm recording. Okay, probably not zooming is much better. Anyway, what is the magnetic flux? By definition, a flux or a flow is when you have a certain directed fluid going into a certain surface opening, you know. You can think of the flow of air current, you can think of the flow of a car out of a tunnel. To be able to find the flux, you count how many cars per second, and then you check the area, how big the area is. This is a dot product, and what I mean by dot product, the angle is very important. So let's assume for the moment that the angle is 0. In other words, you're going into the tunnel in a perpendicular way. You're not going, this is a tunnel and this is a flow of cars going at a certain angle. So let's assume this is stupid and this will give you a very small flux. I'm gonna take only the example just to make your life easy at the moment where the flow is perpendicular to the surface of the tunnel. All right, so I'm gonna take B inside a solenoid and the cross-sectional area. B is mu0 and I. This is mu0. By the way, you multiply by K if you have an iron core. If it's empty, no need to multiply by K. You already know mu0. N is the number of turns per meters or per unit length, and you already know this equation. I is the current. Now, what about the area? I need somebody to tell me how to find the area of a cylinder like this one, the cross-sectional area. Any idea?
Of the cylinder or just a circle?
2 pi r times n.
All right, 2 pi r is not area, it's circumference because it's in meters. It's pi r squared, yes. Yes, Ratib. So you take pi r squared. I mean, it's not the area of the cylinder, it's the area of the cross-section. So imagine you're cutting the cylinder into coins, like pepperoni coins or carrot coins or simply coins, you know? So the area of the coin, you know? We call it cross-sectional because I'm actually cutting through it in a perpendicular way. Because if you cut not in a perpendicular way, you will end up with elongated circles and not real discs, you know? All right, so if I do B times A, I'm gonna end up with mu0 Ni, right? N is big N over L, so big N over L. The area is still here. And all this is multiplied by N because I have, the flux is actually not B times A, it's also times N, how many circles I do have. So I end up with N squared. All right, so if you really look into this equation, I want you to help me pick which items are variables and which items are constant or characteristics of the coil. For example, mu0 is a constant, right? What about N? You say I is a variable. How about I take I in blue? Okay, so you said that N is a constant. What about the area? Area is a constant. What about the length of the wire? It's also constant, which means I can write this as a constant times I, because I is a variable. I can put anything, any current I want. This constant, we decided to call it L, and L means inductance. It is a characteristic of the coil. So when you go and buy a coil, and I don't know if you remember from lab 8, I was showing you the coils and there's something L on it. I told you this is not the length and it's the inductance, and ignore it for the moment. Do you remember? When you buy a coil, N is known, area is known, the length is known. So they give you L and it's a positive constant that you cannot change unless you break the coil or you throw it in the garbage and buy another one. Now, do you remember? Yes, it's the property of the material. It's related to the pure characteristics of the material. Like R, it's a positive constant. You cannot change it. Do you remember the unit for the inductance L? Weber is...
Isn't it Henry?
Yes, it is Henry. So Weber is actually for the flux, and for the L inductance, it's Henry. So when you look at the coil, you would see that it was something like 12 Henry or something like that. Okay, I'm putting back my video because I don't want you to struggle watching the screen. At least you can see my face. All right, so anyway, this is called L in inductance. The bigger the L, the stronger or the lazier the coil is. So instead of the current being established in a moment, it's gonna be very selfish. It's gonna be delaying the current even more. It's gonna oppose the current even more. It's like inertia, you know. If you have a very big mass, a very heavy, I don't know, student, and you want to push the student, it will take you a lot of force to be able to speed him up, right? It's exactly like the coil. So the bigger the L, the more inertia, the slower the process. All right, now Faraday's law, and by the way, you don't need all that, but it's good to understand what's happening, and it's a good review for you. Faraday's law states that the coil itself will give you an EMF. An EMF means a very tiny battery that would be related to the change of the flux over time. And what's changing here is the current. When you have this circuit, for example, and let's say this circuit, oh, sorry, this circuit, it was zoomed in. And let's say somebody said use a switch, and I totally agree. Let's say you open the switch, and let's say you close the switch suddenly. The current goes from 0 to I max in one shot. And this sudden change will induce, this sudden change will give you that delta phi will change, the flux will change, because I will change and B will change, and so is the flux. It will change with time. So just a second, I'm trying to scroll. And the EMF is opposite to the change. So change positive means flux increases. If the change is positive, EMF is negative. If the change is negative, EMF is positive. So this is due to Lenz's law that explains that the coil always acts in an opposite way to the change. This is a way to write Lenz's, the EMF again. EMF is small e. By the way, the unit is volts. Remember, it's a mini battery. If you plug flux is Li, and Li is all this, right? Or how about we keep it Li? Just put here L times I. L is a constant, so you can put it out. N can go in, no problem. So it will be L. By the way, N is, so how about I do all this to be a constant? I'm gonna put it out, and I is the only variable. I'm gonna keep it inside the delta. And delta can be written as a small d if I'm talking about a small change in time. So it will end up being the derivative as a function of time, okay? So this equation is written again. I'm just replacing Li, or all this equation under delta. Everything will go out constant. The current is the only variable. It will stay inside. Do I make sense? All right, so far what we took from this slide is this following. How to find the EMF across a coil, all right? As you can see, when the current is constant, what happens to the EMF? I love this question. Let me try to write your answer. If the current is constant, what happens to the EMF of the coil?
Should be 0.
Yes, current constant, the derivative goes to 0. Yes, which means that EMF is 0. So 0 means what? It means that the coil does not do any induction. The coil acts like a very lame, stupid wire that does nothing. Worst case scenario, it's gonna heat up a bit and acts like a resistor. So this only functions. EMF across a coil means that the coil have a resistance. No, no, Joe, let me try to explain. The coil, and probably grab a pen, the coil has two things. It has an inductance L and obviously a resistance R, because any wire has a resistance R. The inductance L will actually function only when you have a change in the current. If you have no change in the current, you will have to forget that you have an inductance L. And the inductance L is the one responsible to give an EMF. And if you have no di over dt, you have no EMF at all, which means R is not the one responsible to give you EMF, it's the L. R will only give you a heating up of your wire and energy lost in the environment. Okay? So every inductor has an L and an R. The R will make the coil to heat up, so it will take part of the potential difference, and L will be the one creating the EMF. If the current is constant, no EMF at all, and the coil will act like any simple wire, okay? All right, now I want us to discuss a bit Ohm's law, and here I'm gonna create a table because I want to do Ohm's law for different components in the circuit, just as a review. And mind me, this is like what? Grade 11 material, grade 12 material. Okay. So I'm gonna discuss the generator, G. I'm gonna discuss the resistor, and okay, I failed. This is a stupid table. How about I talk a bit about a generator? No, let me start with the resistor because the resistor is easy to discuss. Okay, I'm gonna be a bit advanced. I'm gonna call this A. I'm gonna call this B. I'm gonna make sure that we know the direction of the current like this. This is called R. Now my question for you is, UAB, is it equal to what? What is Ohm's law for a resistor? I know the answer is simple, so it's not a trick question. It's Ri. Is it plus Ri or minus Ri? Can you tell looking at A and B and the direction of the current? The current is flowing from A to B, so UAB is positive Ri, not negative, which means that UBA is gonna be negative Ri, okay? Probably you know this, probably you don't. This is only to make a very important point, okay? So follow the flow of the current. UAB is positive Ri. Now I'm gonna try to do probably something similar to a battery. And I don't know how you covered this in high school, because personally with my high school students, I keep on changing everything. So you tell me, if usually the current goes from here, how do you write the voltage or the potential difference across the generator? And what do you call it? UPN, UNP, anything you remember from high school? Let me use it. Yes. What is the voltage across a generator? Let me give you a hint. This generator has an EMF E and a very tiny internal resistance R. We call it E, right? But what if it has R? And which is E? Is it UPN or UNP? All right, so it's E minus Ri, E for the EMF of the battery, and Ri because some potential is lost, potential difference due to the internal R, and this is UNP, no, this is UPN, okay, positive, negative. This is what you should know from high school. UPN and not following the current. Okay, a second battery, it depends. A receiver, okay, a receiver, I would say, let's put a second battery and the receiver away for the moment. I don't want to confuse you, all right? So, for the generator, a lot of you would say E minus Ri, a lot of you would say Ri minus E. I just want to make a point. If you want to write E minus Ri, make sure it's UPN equals E minus Ri. Now I'm gonna take a coil, and remember, the coil during the inductance will act like a battery. It has an inductance L and R. Okay, so I'm gonna do the following, probably show you A and B. By the way, I'm not happy with one thing. This is opposite to the currents. I want to write this equation again. By the way, can I remove this circle? Come on, if I do this, okay. All right, I want to write UNP if you don't mind. Can you help me write UNP? Because I want to follow the direction of the current to make my life easy. If UPN is E minus Ri, this one is gonna be Ri minus E. Thank you, Ludovic. Okay, please, everybody's welcome to write in the chat. I love chatting with you. I would be really grateful if you can talk to me, but it's okay. I'm not gonna be the drama queen tonight. Okay, so I'm gonna do exactly like this. Now the current is flowing from A to B. All right, I'm gonna say UAB. Remember, the coil is acting like a generator. I'm gonna write exactly this. Okay, so I'm gonna say it's Ri minus E, but I'm gonna call it small e. Do you remember the small e was equal to where's small e? It's here. It's minus LDI over dt, right? So I'm gonna say it already has a minus. Yes, the internet is slow, that's why you're not talking. So Ri, and then you have a minus, and inside the E you have another minus, so you end up with plus LDI over dt. I want you to remember this. From now on, no, the dt. From now on, when you have a resistor, you say this. When you have a generator, you say this. And whenever you have an inductor, you say this. And the three of all these are under Ohm's law. So for me now, I have 3 Ohm's law to think about. The one for the generator, the one for the coil, and the one for the resistor. Also, at any moment, they can tell you that the generator is ideal, so no R. At any moment, they can tell you the inductor is pure, a pure inductor, although in real life, nothing is pure. So no R as well. But if I'm gonna take any example, I should have L and R and E and everything. All right, is that too confusing for you? Let me know if you have questions, please. Now I'm gonna use this slide to write the law of addition of voltages. Let me remind you, I have a generator, I have a resistor R, and I have the coil L, or let me call it L. I'm sorry for my ugly circuit, L, comma R, because it has L and R. And this one, I'm gonna call it E, comma, small r, okay? Let's use this as a parenthesis. Anyway. The law of addition of voltages, you mean, Ratib? Yes, so basically what are Kirchhoff's laws? Kirchhoff's laws are basically to say that in series the voltage is additive and in parallel the current is additive, you know? These are the simple rules you learn in grade 7. These are Kirchhoff's rules, but you never use them in terms of Kirchhoff because you are always, yes, so I'm gonna say U generator just to make it so simple because I don't wanna complicate it for you, is U resistor plus U coil. Okay, U coil, I'm gonna call it UL because I don't want you to think it's a capacitor. U generator, I'm gonna write E minus RI. Okay, I'm gonna use small I because it's a variable. And for R, this is the resistor times the current. And for this one, I'm gonna use probably R prime I plus LDI over dt. And what do we call this equation? I love this equation. This is something you learn in the Lebanese or the IB high school. Okay, this is called a differential equation. Why do we call it a differential equation? Do you understand? What is a differential equation?
It's because it has a variable and its derivative.
Okay, it has a function and the derivative of this function. And how do we solve the differential equations? Is there a way to solve them? You know, any equation you can solve, for example, if I say x squared minus 1 equals 0, the solution is x equals what? What's the solution for this one?
Plus or minus 1.
Yeah, thank you for saying plus or minus 1. All right, so yeah, probably Laplace is one way to solve, and you guys probably you're doing at the moment something related to differential equations in math because I did that long time ago. All right, I remember when I was a junior, we took a course in math and the teacher was so blunt and he was like, listen, you have a recipe for every different differential equation. If the differential equation looks like this, this is the solution. If the differential equation looks like this, this is the solution. And we had to remember all these recipes and it was crazy for me. Let me show you a different differential equation. Have you ever saw this one?
One in mechanics?
Yes, is that a differential equation?
Yes.
All right, so x is the function, the time equation, so it's a function by itself. And x double prime is the double derivative of it with the function of time. So the question is, what is the solution? And Ratib said it's a sinusoidal solution. So this one has a sinusoidal solution because it's a differential equation of the second order without the first order, and the coefficients are positive. So there's a recipe that says if you have an equation like that, you will end up with a sinusoidal equation. Yes, Wt or y equals something Wx. If you have a differential equation like this one, where this is a first order, and you don't have a second order, and it's positive, what do you remember?
Exponential.
It is exponential. Thank you so
Exponential.
much. Yes. If it's equal to a constant e, it's going to be an exponential increase. If it's equal to 0, it's going to be an exponential decrease. So now I'm going to go to the exponential solution of the current. I don't want you to freak out. It's only a recipe that states this differential equation will give you this solution, and nobody knows why, but you can prove it easily actually. So now behavior of the current, and now I'm very close to the actual experiment. All right, so this is, just a second, trying to scroll. This is a circuit. The switch can be on 1. When the switch is on 1, I have a regular RL circuit where I have a current. Please mind the vector. The vector means nothing because the current is flowing in this direction. And you know, the inductor or the coil will oppose the establishment of the current. أكيد رح يقبل بالآخر, but the first few seconds you will have a slight delay in the current. وبعدين عادي. Then the switch will go to 2. This is where the battery disappears suddenly. So the generator will start giving 0 voltage. And this is where the coil will not be happy about it. And the coil will gonna oppose 0 current. So the current will go to 0, but the first few seconds, you will have a tiny little light if you have any bulb in here, or a tiny little current if you have an ammeter to measure it, until before it goes to 0. So whenever you have a generator or your differential equation is equal to E, you have an exponential increase, and this is an exponential decrease. Also, this behaves like an RC circuit. So yes, we have tau, because tau is not a characteristic of an RC circuit. It is a characteristic of an exponential behavior. Tau, by definition, is the time needed to reach 63.2% of the maximum value. Okay? Tau for the RC circuit was equal to R times C, and tau for the RL circuit is L over R and not L times R. Be careful, R is the total resistance in the circuit, because as you remember from this, you have a resistance inside your coil, a resistance inside your generator, and your actual resistance. So make sure it's R total. And eventually when you reach 5 taus, by the way, I don't like this because usually it's 5 taus until you reach a value very close to 0. So I'm not happy with this reference, but I like the graphs. All right, so this is current as a function of time. How about we do a small practice and try to find tau? That was never my plan, but I just came up with an idea. Who can help me find tau in this one? So tau equals question mark. Let's try. Anybody? Break it
Is it
down.
gonna be 4?
And over R.
So L is not given, L, and R is not given. To find tau graphically, I need to find what is U max or I max, I mean.
Tangent.
Okay, I can do the tangent method and check it out. So this is tau around this value. How about I do U max and find the 63% of U max? What is U max? I mean I max. What is I max? Let me see. 1, 2, 3, 4.
6.25, or rather 6.5.
Yes, I totally agree. So this is 6.5. Can you please try, and the unit is milliamperes. Can you try to do 63% of 6.5?
It's around 4.1.
Okay, 4.1 is very close to 4 because this is 4.5. So it's somewhere here. So probably this. And what does this mean? Tau is equal to how much? Around 50 milliseconds? Yes. Yeah, around 50 milliseconds. I'm not trying to be precise because anyway, the graph is not precise. All right, if I do the tangent method, I really need a ruler. Otherwise, probably Shafit, I was hitting this and this will give me 75. It's not precise. The tangent method is not precise at all, but sometimes you use it theoretically, it will give you good results. All right. Okay, now the equation, by the way, I, the current, is total voltage over total R. Remember, we don't have an EMF at Imax. Imax because you have a constant current in here, so no inductance, no induced, what do we call it? No inductance, anything you want. So the small EMF is actually equal to 0, the one of the coil. Let's call it E of the coil. All right, so this is the equation of the exponential increase. It's I max into 1 minus exponential minus t. T is the variable over tau. This is tau. I need someone to help me find the equation of the exponential decrease. What is the equation of the exponential decrease? I equals. So this is
I max.
So
Exponential minus t over.
Okay, so minus t over tau. Okay, so this is for the decrease, and for the increase it's 1 minus e minus. When I was in high school, I had difficulties remember which is which, and then I thought this one has 1 minus, so it's decrease. This one has 2 minuses, so it's increase. It's only a trick to remember. I don't know about you. All right, now you will be given a very simple RL circuit. Let me show you the experiment. I'm gonna give you this link. It is inside the PowerPoint, so you can watch it. This is my colleague doing the experiment and not myself, so this is not my hand. She was doing it in Beirut. Her name is Dr. Noura. I don't know if you know her. Anyway, I want you to see what's in the circuit. We saw, okay, I just jumped. Yeah. We saw this board before when we did the resistances. You have, this is a resistor, and this is another resistor, and this is a third resistor. She's gonna pick one of the resistors. This is a coil. So under the masking tape, you have wires coiled around a certain plastic material, okay? Let me use red, it's more visible. And the resistance is already connected to the coil. No need to connect them both. So what you need to do, you need a wire to connect your power supply and another wire to connect to your power supply, and that's it. And she will do the connection in the video. You will do the experiment just like this, or you add this iron core inside this one to change the inductance of it, and you're gonna see that the inductance is gonna change. Here, she just inserted the iron core, بس هيك بتحطه. It will touch the table. It doesn't have to have any special connection. You just insert it inside the coil and you do the experiment again. She will connect the circuit to the science workshop, and the science workshop is giving, let me use a dark color, or probably here, it's giving you a squared signal. And what I mean by squared signal, sometimes you have a voltage V and sometimes 0, sometimes V and sometimes V0 in a periodic way with a certain frequency and a certain period. Because we didn't want to give you a switch and you keep on switching on, off. Instead of doing that, we give you a generator that will give you a squared signal that is positive. So V, then 0, V, just to mimic the behavior of a switch, okay? And this is the graphs that she will get. You will see 3 different graphs. She will use 3 different sensors. Usually the students have difficulties understand how the connections of the sensors are. Anyway, this is the generator. You see the squared signal. Probably on the video it will be more clear. This is the exponential increase. So this is exponential increase, and this is exponential decrease, and then increase, and then decrease. Can you tell me which voltage is that? That's a tough question. So all the sensors will actually measure the voltage. The blue voltage. Which voltage is it? So we said that this one, I'm gonna, yeah, across the coil. So this one is for generator, right? This one you said coil. Remember what we studied, the one with the increase and the decrease, was what exactly? It was the current. And if you look at the voltage across the coil is this one, right? So it's not proportional to the current. So if the current looks like an exponential increase, the voltage across the coil does not look like an exponential increase because it's not proportional to it. So I need somebody who is proportional to the current to be an exponential increase and decrease. Who is this somebody? Yeah, or which component in the circuit will give you a voltage exactly? Anthony, thank you so much, Anthony. This is a big deal, you know. So it is U of the resistor. So, and I know probably you should know this from high school, but since you did not do any official exam, it was a very key answer in an official exam in the Lebanese curriculum. What does it say? If you want to visualize, the current, okay, you measure the voltage across a resistor. It is proportional to the current. Okay, proportional to the current. So you guys, and I don't want you to be confused, whatever you have here, this weird signal is the behavior of U across the coil. ما تسألوني ليه شكلها هيك. You never study this actually. أنتوا you study the voltage of the battery and you study the current across the circuit. Now, how do you find this one? U generator is U coil plus U resistor. So you do U coil is U generator minus U resistor. So you will understand why it looks like this. Okay? So you guys never study U across the coil. You only study the equation of it, and it's a differential equation, you know? So you only know the behavior of the general voltage and the main current, you see? And I'm gonna use this, by the way. You see something here like a box, and you see a yellow selection. So Dr. Noura was actually selecting this part, and then here they will give her the exponent, and the exponent is what you have next to the exponential. So when you look at the exponential graph, which is here, the exponent here is 1 over tau. So Data Studio, when you select the graph, will give you directly 1 over tau. So all you have to do is do the connections, run the graph, click record, click stop, then select the curve you want and take the exponent, deduce tau. Repeat this for many trials, the lab is over. This is all you need to do. Find the average, find the RMS, you're done. Okay? Now let me show you the lab report. They will tell you, can I do this? Scroll a bit, yes. Not really. So they will say fill in the table, total resistance of the circuit. I'm gonna give it to you. I'm gonna watch the video again to see if Noura was stating the values. Otherwise, I'm gonna give you the values. Tau theoretical, you were supposed to calculate it. It's L over R total. The fit constant is the exponent. So it's 1 over tau. If I'm not wrong, read the procedure well. You deduce tau, don't forget to write the units. Find the average tau along with the error, RMS. Compare to the theoretical value, they should be very close. Deduce the inductance, compare it to the nominal value. How do you find tau theoretical if you don't have the inductance? Or probably deduce the experimental inductance. So you should be given L and R to be able to find this. So by comparing these two, you can tell if the experimental inductance is different. Compare percentage difference, comment on the sources of errors. This takes around 2-3 minutes. Just you need to find the average and the RMS, and they want you to repeat the exact same thing, but with an iron core. You see the iron core here? So most probably L is gonna be a bit higher. But before I leave you, there's question number 5 that is very important. Does Kirchhoff loop rule hold at all times? Use the graphs to check it for at least 3 different times. Does the sum of the voltages across the resistor and the inductor equal to the source of voltage at any given time? You need this graph. Let me try to zoom in and to scroll. I'm sorry for the delay. It's due to the recording, yes. So you pick a certain time t. Can I have this narrower? Yes. You pick a certain time t. And using the smart tool, you find the voltage here and the voltage here and the voltage here. And you check, is U generator equal to UL plus UR? And you try it for this value. Okay, and you check. So you pick one time that is constant. By the way, these are locked. So if you pick one time, it will give you all the voltages at a constant time. You try this one with this one and this one. Here you cannot really see what's in there. Probably I give you the values, or we can see in if the video is clear. Here it's written UR, but you cannot see it. Here it's written UL and you cannot see it. And here it's written voltage, probably generator, but you cannot see it. Okay, so that's it. Now that you see that now that you see that the lab report is really quick, no plots, nothing, like you have this page and this page. This is all the lab report, not part of it, it's all of it. Do you still need all this time to finish the deadline? Can we submit lab 9 then lab 6? Yes, you can submit lab 9 anytime. You just need the values and you need Jessie to give you the values. That's all. You want to switch lab 9 and 6? I would say why not, as long as I have anything to grade you. Now back to the deadlines here. Help me find a good deadline for lab 9 or any lab you want, but don't say beyond Tuesday, because I need at least few days to be able to correct, and your final exam is gonna be either Friday or Saturday. Yeah, I think Monday is good, because the earlier the better. You want your week to be free because it's your final week, and I don't want you to be bothered with a lab report. And if we ever say that the deadline is Monday, it means try to submit before this deadline. Don't wait until Monday evening. Believe me, you want your final week to be free, because you will have a lot of projects and assignments to submit. And the last thing you want on your agenda is a lab report. How about a very boring and easy lab report? Do it as soon as possible, okay?
Doctor, can we have it on Tuesday? I cannot make it. I cannot do it for Monday.
Of course, we can have it on Tuesday. Remember, those deadlines are for you, and you are supposed to pick the deadlines. All right. So for the
Thank you for understanding, Doctor.
For the students who want that to be on Monday, submit on Monday. Okay. So Tuesday is only an extension for the students who cannot. So do it on Monday and keep Tuesday for the exceptional students. In the finals, we will do an actual experiment. No Ratib. We never did that before, COVID or not. The final exam is always theoretical, and I mean by theoretical, data analysis and conceptual. We believe you usually do enough experiments, and we're already grading you through 50% of the total lab grade through lab report and experimental work. Now I know we don't, it's exactly like the midterm. I think it's gonna be a photocopy of the midterm, like exact copy, but instead of doing lab 0, 1, 2, 3, 4, you're gonna do lab 0 and 5, 6, 7, 8, 9, which is a bit more chapters. It's a final exam eventually, but not the same chapters, okay? So I'm gonna say midterm is a mini final exam, all right? More questions? Multiple choice or not, I don't know. Most probably yes, but I do not know yet. Other questions? How many questions? I don't actually know if it's a multiple choice. How can I tell how many questions? It will take me forever to create your exam, you know? Let me create some practice worksheet for you first, then an exam. I need to create both. So I don't know how many questions. And probably I can never know before one day before the exam. Anything else? I'm gonna stop recording, and please feel free to ask any question. And please, please, please